Discussion on the fluid mechanics and thermodynamics review. So, what we have been talking about that the control mass and control volume system, and how Reynolds transport theorem can be applied to derive all the basic conservation laws. And if you just recall from the last lecture, this is what we have shown, that for a different property and how you can derive all these different conservation equation. And we have with this particular one, we have talked about the mass conservation equation or rather continuity equation and how to reach the incompressible limit. So, now we will look at the similarly momentum equation. Now, one can always derive this like what is typically done in any fluid mechanics course or any fluid mechanics book, that taking a elemental control volume and you can derive, because it is nothing but the Newton's law of motion, F equals to m a. From there one can derive the same set of equation, but the idea here is not to derive in that fashion, rather looking at the things from point of view of the RTT. Now, so here n would be rho and eta would be velocity vector for momentum equation. So, what one can write that d rho, this is n is if you see n is, this is the forces, let us say vector. So, this would be forces. So, d rho by dt for control mass system, which is nothing but the all the forces, that is summation of all F s plus F b. So, F s is surface force, and so these are act at the boundary of the control volume, like for example, reaction forces, pressure forces, shear forces, these are all surface forces, and F b is the body force. So, these forces are acted on the material inside the control volume, and this could be proportional to the mass or the volume of the fluid. For example, gravitational forces, electrostatic forces, electromagnetic forces, like that. And this F is the sum of all the external forces which are acted on that particular. Now, this F is del T of, so control volume rho v dv plus control surface v rho v dot dA. Now, if we say, let us say the body forces are B and all surface forces we can like T dA, these could be pressure, shear stress, something like that, then what we get is that control volume B rho dV plus control surface minus P dA, which is ddt of control volume rho v dV plus control surface v rho v dot dA. Now, this one particular one we can write like control volume delta dot V rho V dV. Then what we get finally clubbing this term, and this also we can use, and then finally what we can write del T of rho V plus delta dot rho V V equals to minus del P plus del dot tau plus rho F. So, this is what you get from that. Now, similarly, this is in vector form. One can write this equation in also indicial notation, and that would look like, just for your reference, I am just providing that thing, but you can look at any of these fluid mechanics book to review this derivation or the different notation for the same. So, these are now we look at the energy equation, and for energy equation also you can derive similarly, but for that we just look at the first law of thermodynamics. So, it accounts for the rate of change of energy of either a system or a control volume. So, what it states that the net heat added to a system should be equal to the sum of the change in stored energy of the system and the work done by the system or the surroundings. So, typically if you let us say have a system like this, then the heat added here, this is the work output of the system. So, when heat is added, this should be positive, when the work is output, that should be also positive. So, we can write the delta E naught plus W, where E naught is the stored energy, which is E k, E p, E I e, and in differential form. So, you write dq minus dw equals to d E naught, and per unit mass E naught would be energy per unit mass. This is kinetic energy per unit mass. This is potential energy per unit mass, and this is internal energy per unit mass. So, we have all this terminology, and also one can write that this E naught should be V square by 2 plus Z z plus E, which is nothing but E naught by m. Now, there are two kind of work. One is the flow work, which is work done on the surroundings, and second would be soft work. So, the soft work is the any other form of work, for example, work transferred through the control surface by shaft, electric current, etc. Now, similarly, if we use the RTT, so we write d E naught by dt would be del T of control volume E rho dV plus control surface E rho V dot dA. So, you put things back there, and so this once you take the divergence and all this. So, what you can look at those couple of steps further for detailing, and you get back del T of rho E naught plus delta dot rho V E naught, which will be dq by dt Ws by dt by dt. So, here W P is control surface, P by rho V dot dA. If I write in control volume, del dot rho V P by rho dV. So, the equation transform back to rho E naught plus del dot E V E naught plus P by rho dq by dt minus dw by dt. So, this is shaft work and heat transfer. So, since E naught equals to E plus U square by 2 plus dz. So, one can write it back del dot rho V H plus V square by 2 dz equals to Q minus W. So, that is what you get. Now, if you look at, so this derivation also one can do in a conventional approach. Now, quickly what second law of thermodynamics states, it is talk about the entropy, and what if your process is reversible, then this can be written as for reversible process, and the ds is the change in entropy in a reversible heat exchange of dq and a temperature T. Now, if it is an irreversible process, then ds would be always dq by T for irreversible process. Now, if the process is reversible and adiabatic, then dq is 0, which means ds is 0. That means, there is no change in entropy. So, this process is called the isentropic process. Okay. And the second law is used to basically describe the ideal operation of an engine for the calculation of efficiencies and other parameters. Now, some other thermodynamical property of the gases, like again if we look at from first law, what we can write, dq equals to dE plus dW. Now, for reversible process, we can write dW equals to P dV, and then the Gibbs equation becomes P ds equals to dE plus P dV, and the perfect gas equation states that P equals to rho RT. Okay. And we can write the, so if these are thermally perfect gas, then E would be only function of temperature and H would be E plus P by rho. So, which follows that H is function of temperature. Now, the definition says specific Cv is d by dt and Cp is dH by dt. So, what we get, H equals to E plus P by rho, which is E plus R t. Now, if I take dH by dt, this is d by dt plus R, which means Cp equals to Cv plus R. So, if you take both sides with the, so Cp minus Cv by Cp equals to R by Cp, which would be 1 minus 1 by gamma R by Cp. So, what we can get, Cp is gamma R by gamma minus 1, while Cv is R by. Now, some other equation what we can write, like from the T ds is dE plus PdV. So, that gives me that H also equals to E plus P by rho. So, or rather H equals to E plus P V. Then we can write dH equals to dE plus PdV VdP. So, which is TdS equals to dH minus VdP. So, here dE plus PdV, this one can use this relationship here, and so this is dH minus dP by rho. So, if you divide both sides by T, this would become ds by, so you get ds equals to dH by T minus dP by rho T. So, you write ds equals to dH by T minus dP by P. So, we can write like dH equals to Cp dt. This is for calorically perfect gas, calorically perfect gas. So, there are two types of situations, one is calorifically perfect, another is the thermally perfect. Once we use this relationship, so for isentropic process, this should be ds equals to 0. So, what we get, it's Cp dt by T equals to R dP by P. Now, we can do the integration on both sides for constant specific heat. What we get, Cp ln T2 by T1 R ln P2 by P1. So, ln P2 by P1 ln T2 by T1. So, that gives us back P2 by P1 is T2 by T1 to the power Cp by R. Okay. So, these are the sort of relationship that one get from this. Now, we have already seen some other relationship, like what we have seen Cp is R gamma by gamma minus 1 and Cp by R is gamma by gamma minus 1. Then this ratio of P1 by P2, we can write rho 1 R T1 by rho 2 R T2. So, T1 by T2 whole to the power gamma by gamma minus 1, one can write rho 1 by rho 2 T1 by T2. Okay. Now, since we have P2 by P1, T2 by T1 gamma by gamma minus 1, which is Cp by R, what we get rho 2 by rho 1 equals to T2 by T1 1 by gamma minus 1, or P2 by P1 equals to rho 2 by rho 1 to the power gamma. So, this is what you get the relationship for all the isentropic process where there is no change in entropy. So, keep that in mind, these are only for isentropic process. Now, for if we have for non-isentropic process, what we can write S2 minus S1 is Cp T2 by T1 minus R ln P2 by P1. So, that you get from this equation and getting the integration between two points, you get that relationship for non-isentropic process. So, if it is a constant pressure, for constant pressure, this delta S is Cp ln T2 minus T2 by T1. So, that either you can show it from here using this equation for constant pressure, or you can draw a sort of TS diagram like this, and so this is let us say P equals to P1 here, P equal to P2 here. Now, this is on the constant temperature line. So, if the temperature line is constant, this delta S would be minus R ln P2 by P1. Okay. So, these are some of these relationship that is commonly used for different kind of processes, and you should be aware of that. Now, with that brief idea, I mean, now the whole idea is that you can review all these details. These are just to sort of refresh your memory about all this. So, you can look at any other textbook and all this just to go into the detail. So, we will move to that, the discussion on compressible flows. So, now what important thing for the compressible flow discussion here, what we will be discussing here, the working fluid is, so working fluid is to be perfect gas. So, that is one of the thing that, so whatever thermodynamical relationship that we have just looked at, they will also be true and can be used. Second important things for compressible flow is that density is no more constant. So, this is a variable density situation and it changes quite drastically. It is not like that it remains constant. Now, the first thing which comes is speed of sound. How do we define speed of sound? It is just like air is composed of molecules, they are moving in a random motion, but they have a mean velocity and average energy, which is quite known. Now, sine waves are sort of weak pressure wave. So, sound waves are weak pressure waves and they are carried by moving air molecules. Now, when there is a source of sound, it releases some energy which is usually picked up by the neighboring molecules and causing an increase in their kinetic energy. So, obviously, if there is a source which emits the sound wave or the noise, so these are picked up by this particle surrounding it, and once they pick up that, so there would be increase in the kinetic energy. Now, this kinetic energy which is picked up by the neighboring immediate neighboring molecules, they are transmitted from one molecule to the another molecule, and this process of this transmission happens through molecular collision. So, this sound energy which is from here, it gets transmitted through the molecular collision. So, the pressure wave is generated due to that. So, this pressure wave is generated by the source, is transmitted through the molecular collision. So, when that happens, our eardrums actually pick the variation of pressure wave. So, there this variation of pressure waves, these are picked up by our eardrums and it passes by and our brain sense it, thus we actually hear the sound. This is how actually we are able to hear some sound which is generated somewhere else. Now, this transmission of sound is accompanied by change in pressure, density and temperature. So, Newton provided a expression for estimating the sound wave, which is del p by del rho at T. So, this is where it was considered to be an isothermal process, but later on it was found that this transmission of sound waves through air or any gas is an, so transmission through any gas is an isentropic process, which means the definition would be del P by del rho. So, this is what the definition which was kind of given later on. So, and then since it is an isentropic process, we can see how one can estimate the sound wave from here. So, we will just stop the discussion here and continue in the next lecture.